Welcome back to the third lecture of environmental economics. This week is about the social cost of carbon and carbon pricing. Last week we saw that neoclassical economics proposes to introduce taxes or cap and trade type of emission allowances that price externalities at their marginal cost in the social optimum. You may remember that public goods or its negative counterpart, public bads, and the tragedy of the common, can be recognized as special cases of the more general externality problems, where external costs are ignored in determining privately optimal behavior. Today, we dive deeper in these two instruments of Pigouvian taxation and cap and trade and comment on their relative merit. Today, we start with a discussion on the practice of estimating social cost of carbon. We begin this review with the integrated assessment models, borrowing from Nordhaus' Nobel lecture. This is followed by a set of critiques from Pindijk. Next, we leave the imaginary world of optimal consumption paths and look into Stiglitz, Stern and the High-Level Commission on Carbon Prices, their assessment of Paris-consistent carbon prices. I close with some thoughts from Maestre Andres about the public acceptability of carbon pricing. The figures on the slides are borrowed from Ed Hawkins and depict the increase of global temperature since 1850. We will start this overview with William Nordhaus' Nobel lecture from 2019 for the 2018 prize in economics. Nordhaus' contributions have largely been in developing a specific integrated assessment model, the Dynamic Integrated Climate Economy Model, also referred to as the DICE model. These type of integrated assessment models are used to estimate the social cost of carbon. The social cost of carbon are an important input in determining the appropriate level of carbon prices. Cody and co-authors describe social cost of carbon, SCC, the discounted value of worldwide damages from future global climate change associated with an additional ton of current emissions, where discounting refers to the practice in economics to give lower value to impacts that occur further in the future. An alternative definition by Toll reads, the social cost of carbon is defined as the monetary value of the first partial derivative of global net present welfare to current carbon dioxide emissions. It is sometimes calculated as a true marginal along a welfare optimizing emissions trajectory, and so equals Pigou 1920 tax on carbon dioxide. Nordhaus describes as advantages of using integrated assessment models that these combine the insights from different disciplines and give internally consistent estimates of the social cost of carbon. The prototypical model is a constraint maximization problem that maximizes a consumption path over time, subject to a set of constraints that model climate and economy, where Nordhaus describes this notation as CT is consumption, YT are other endogenous variables such as global temperature, ZT are exogenous variables such as population, alpha are parameters such as climate sensitivity, rho is the pure rate of time preference, and epsilon t are random variables in the stochastic versions. The discounting in continuous time gives slightly different notation than discounting by year that more of you will be familiar with. Yet, with a bit of training in mathematics, discounting with continuous time is easier to manipulate. So how are these estimates for the social cost of carbon obtained? Nordhaus describes on page 2000, here is the basic intuition. The DICE model estimates the path of the economy that optimizes consumption, emissions, and climate change. These calculations take into account the production functions of the economy, the constraints of the carbon cycle, and the rest. One of the auxiliary byproducts of the calculations is an estimate of the impact on optimized consumption of an extra ton of emissions. For example, an extra ton of emissions might lower current consumption by $40, holding consumption in other periods constant but respecting all constraints. I pause to note the source of this idea. Research of Kantarovis and Koopmans showed that the optimization of a linear programming problem produces both primal variables, here emissions, and dual variables that show shadow prices, here the impact on the objective function of a unit change in emissions. The DICE model produces the shadow price as a part of the solution. The shadow price is a mathematical variable associated with carbon emissions in an optimized framework. Later, this was interpreted as the carbon price or carbon tax associated with internalizing the carbon externality. So, in other words, the DICE model obtains estimates for the social cost of carbon as byproducts or dual variables of a constraint optimization problem. I will first try to illustrate this idea of shadow prices, and I will later show how the focus on an optimal consumption path may also be considered a weakness of the estimates. Comparable to the constraint optimization problem presented by Nordhaus, we see that some function f needs to be maximized by choosing x1 and x2 subject to a constraint g that also depends on these x and needs to be equal to c. This maximization problem is similar to that of a consumer that wishes to maximize utility subject to a limited budget. Possibly you recognize that we find its maximum where the objective function finds tangency with the constraint. This maximum is also expressed by the first order conditions, where this slide shows that after rearranging terms, one can introduce the Lagrange multiplier lambda. The advantage of this Lagrange method for constraint optimization is that these lambdas have an interpretation as described by Nordhaus. These lambdas can be interpreted as the shadow prices of the different constraints. In other words, the shadow prices are estimates of the marginal effects of relaxing constraints on the objective function. Let us make the translation back to Nordhaus's model. The shadow prices are the marginal effects of climate-relevant constraints in the model on the optimal consumption path. In a 2018 publication, Nordhaus defines the social cost of carbon as the marginal effects of emissions on consumption, and note that these change over time. Now that you know a little bit more about the models used to obtain these estimates, what estimates for the social cost of carbon does Nordhaus present? Table 2 from Nordhaus shows that the estimates strongly depend on the choice of discount rate, where we see social cost of carbon close to $1,000 for near zero discount rates, and that these estimates drop rapidly for higher discount rates. That is, if the future receives less weight, as is the case with higher discount rates, the social cost of carbon are considered lower. Nordhaus's favorite estimate would call for a carbon price of slightly over $40. So what is a discount rate, and why do we discount? And which rate is appropriate, you may wonder, especially if you are a student from outside of economics. The discount rate refers to a rate used to express future flow values in discounted current terms. In other words, this rate determines how we weigh the present in comparison to future outcomes. A brief starter on discounting is Arrow et al. 2013 that argues for using discount rates that decline over time. So what are reasons for discounting? Discounting concerns trade-offs involving the present and the future. Arrow et al. 2013 explain on page 349, there are two rationales for discounting future benefits, one consumption and the other investment-based. The consumption rate of discount reflects the rate at which society is willing to trade consumption in the future for consumption today. Basically, we place a lower value on the consumption of future generations because we assume that these future generations will be wealthier than we are and that the utility people receive from an extra dollar of consumption declines as their level of consumption increases. The investment approach says that as long as the rate of return to investment is positive, we need to invest less than $1 today than to obtain $1 of benefit in the future. With the declining discount rate schedule, benefits and costs in a given year are discounted at the same rate, but the rate declines over time. Arrow et al. Argue for the adoption of a declining discount rate in benefit cost analysis of projects with long time horizons because, as it says on page 349, uncertainty about future discount rates leads to declining discount rate schedule. That uncertainty about the appropriate discount rate gives a declining certainty equivalent discount rate approaching the lowest of the discount rates considered for the distant future was proven by Martin Weitzman. The intuition is that expected value of discounted sums depends increasingly on the lowest discount rate considered as we move farther into the future. Even though discounting future impacts is standard practice in determining viability in public cost-benefit analysis, the concept of discounting future utility is not without controversy. There are also many economists that call to use near-zero discount rates when it comes to projects that concern the distant future, such as climate mitigation and adaptation. It is my impression that this call for lower discount rates is increasingly embraced, especially in this time of near-zero interest rates. You can read from the quotes that Ramsey considered discounting a weakness of the imagination, and an excerpt from Anand and Sen hints at how Ramsey got around the issue with convergence without discounting by introducing a maximum possible obtainable utility level called bliss.